Now that you're armed with this powerful tool, the point charge, and you understand how it impacts the environment in the vicinity of the charge, the logical extension of the problem is to tackle more realistic charge distributions. Before you consume this video, you're going to have a look at page 33, titled Distributed Charge. This lays out the basic ideas in the problem-solving process laid out in some clear steps at the bottom here. Now let's take this most basic problem, which is given on page 34. The problem where charge is distributed over what we'll call a uniform rod, or uniformly charged rod of length L and charge Q. Creating a realistic sketch of the object doesn't have to be fine art. This is the most important step that you can imagine for obtaining success on an exam. In any exam paper that I grade where the solution is not attained, I can usually trace the problem back to either the complete absence of a sketch of the problem or a sketch that does not fully label the quantities that are relevant to the particular solution. So we are asked to go to this location P, which is a distance d away from the left end of the rod, and determine the electric field, which is created by this uniform distribution of charge. So we can sketch out shading here to indicate that distribution is even throughout the length of the one-dimensional object. So step one of your problem-solving process on page 33 dictates that you draw this picture and you label some chunk of charge. So I'll take this chunk here. You're going to label it dq. Why dq? We're not taking a derivative with respect to anything. You need to understand throughout this course we're going to be using the calculus differential dq to mean here the smallest possible quantity of non-zero charge. It is entirely equivalent to your first exposure to a differential, probably dx, in a calculus course. Here the width of this dq, the width is dx if we take this to be the x-axis, and our object only extends in one dimension along the x-axis. We draw it with some thickness here, but we don't want to take that into account for the solution of the problem. So it has a width of dx. It's the same calculus differential that you know and love, where shading the area under a curve becomes a problem of drawing thin trapezoids beneath that curve and then allowing the width of the trapezoids to shrink in a limit where the width goes to zero. It does not equal zero. It attains this differential or infinitesimal width, which is the smallest mathematical quantity that you can deal with. Make sure you get comfortable with the differential quantities, physical quantities of length, charge, current. We're going to use them throughout this course, and you should definitely ask in class if you're concerned with your understanding of the differential quantities. So we have our dq labeled. Why should you not pick the endpoints or the symmetric middle of the object? Those are fine locations. There is a dq at those locations, but you'll be tempted then to label the r, which is going into your solution. You're going to be tempted to label it incorrectly. You're going to be tempted to label it as a constant. So what is this distance r? Always in our expression for a single point charge, the electric field was in magnitude kq magnitude over r squared. So this r is always the distance from the charge q to the location where you want to know the E field. We're calling that point P here. For a differential charge, dq, we will write that it creates a differential contribution to the electric field. We're just talking about the vector magnitude for the moment, equal to k dq is the amount of charge over r squared. Picking a dq, which is at the end, is going to tempt you to throw d into the variable distance r, and that will get you an incorrect result in the end. We need to allow for r to describe the distance to any location of a dq anywhere along the length of the rod. Okay, step 2 in your problem-solving process is to pick an axis system. We're treating this as a one-dimensional problem. It's a linear charge distribution. We'll look in the next video at a curved linear distribution in 2 dimensions. Our axis is simply x, pointing positive to the right. We'll choose our origin to sit at the location where we want to know the electric field. Then the left end of the rod is located at x equals d, and if the length of the rod is L, then this right end of the rod is located at d plus L. Our picture is set up. We have an axis system. We have drawn step 3, draw the variable r that extends and defines the distance from the point P to the location of the charge, dq. We will express dq in terms of a variable x and a linear charge density, lambda. Whenever you read the words uniformly charged in one dimension, your mind should go to the lowercase Greek letter lambda. For a finite object here, the charge per unit length is Q over L. You can see its units will be coulombs per meter in one dimension. This is valid for the uniform case. For the non-uniform case that we'll look at in class, you will need to allow that lambda to have a variable density which depends on the location x. So how much charge is dq? I told you earlier it's the smallest amount that you can imagine, but here we're asked for an amount of charge dq in step 4 of the problem-solving process. This is lambda, how much charge you have per unit of length, times the length of the dq, which is dx. In every expression that contains a differential, you must have a differential on both sides of the equation. So the small amount of charge dq is the amount of charge you have per unit length times the length of the dq. Here that's dx. Step 5, write an expression for dE, the electric field, which is due to the dq. So at location P, we have a vector. We're going to assume here Q is positive. In every problem we give you, you may assume that the charge is positive unless we tell you otherwise. So we should create an electric field vector, dE, which points away from that positive charge to the left in this diagram. It has a magnitude, K magnitude dq, over r squared. In terms of our variable x, then, where is the dq? It's everywhere along the rod. It has to allow for any value x between d and d plus L. So we have k magnitude lambda dx divide by the distance r squared. Here that distance is just x. And because we assume the charges are positive in this problem, we can drop those absolute value signs. So k lambda dx over x squared is the magnitude of that dE vector. You can tell there will be an infinite number of these dq's along the length of the rod. Each one will create its own contribution to the electric field at point P. All we're doing is, by vector superposition, adding the electric field contributions from each dq. You saw in the previous video an example with 2 point charges. Well, now we're just doing it with an infinite number of point charges. Since we don't want to be here all day, we will use the power of the calculus to perform that infinite Riemann sum. The integral symbol tells you add up all of those dE's. We can play fast and loose here with vector components. That was step 6 of the problem solving strategy. Here it's a one-dimensional problem and every dE vector points away from the relevant dq. So they all point in the same direction and their magnitudes will simply sum together. I'm going to pull out the constants, the things that do not depend on position x. So we have k lambda integral dx over x squared. The limits of integration should cover all of the possible locations of dq. So we're going from x equals d up to x equals d plus L at the upper limit. Now this is k lambda. Integral of 1 over x squared is minus 1 over x. And we'll evaluate from d to d plus L. Minus k lambda, 1 over d plus L, minus 1 over d, or could write it positive k lambda, 1 over d, minus 1 over d plus L. Well, this is step 7. Get rid of any extra variables you defined. Was lambda given in the problem? No, it wasn't. It was a tool that we used, an intermediate variable along the way. So we should eliminate lambda in terms of the givens, which were q and L here. kq over L, 1 over d, minus 1 over d plus L. You could massage the fractions here if you want to make your expression as simplified as possible. We have completed step 8 of the problem-solving process, which was to determine the integration limits and integrate. Here we only have an x component. Now we're going to create a common denominator, make it look a little nicer, so we have d plus L minus d divided by d times d plus L, or k q over L over d times d plus L. You see that L's cancel out. KQ divided by d times d plus L. It's the magnitude of a vector. It better be positive. Is it? Yeah, looks good. D and L are both positive quantities. Let's check our units. If you have time on the exam, you should always check the units of your result. If your units are wrong, you know your answer is wrong. If your units are right, you're going to have a pretty good sense that you're on the right track. You could have some numerical constants incorrect, but if your units are right, you've probably done the problem correctly. K has units Newton meter squared per coulomb squared. Q is just coulombs. D is a distance, meters. D plus L is another distance, meters. So you have meters squared canceling out, and we're left with newtons per coulomb, which is the desired units of electric field. What are the limits, the limiting behavior of every solution you get? It's going to tell you a lot about the physics, the ultimate meaning to your abstract mathematical expression here. If you go very far away from this object, in other words, D becomes much, much greater than the length of the rod itself, what happens to E? The electric field, you see, we can ignore L when it's added to D. It becomes, or approaches, KQ over D squared. Does that look familiar? It looks exactly like the electric field of a point charge. In the opposite limit, if the rod becomes much longer than the distance d from the end of the rod, you might call this a semi-infinite line. Well, a uniformly charged semi-infinite line has infinite charge. Just allow that L to go off to infinity. So you should really think about it, or go back to the idea of lambda, charge per unit length, and what happens in your expression now. You had k lambda times 1 over d minus 1 over d plus L. This term goes to 0 when L is very large. You just have k lambda over d. And we'll include here a check to the numerical approximations that were made in class on page 31, with a lambda of 60 nanocoulombs per centimeter. In that problem, you were given 480 nanocoulombs and a length of 8 centimeters. This is 6 10 to the minus 6 coulombs per meter. The distance d in that problem was 5 centimeters. And the length, as I mentioned, was 8 centimeters. You plug this all into your calculator, and you end up with an electric field magnitude of 6.64 times 10 to the 5 newtons per coulomb. And that's exactly what we expect coming out of that problem. To set up a related problem, let's step into the two-dimensional realm. Imagine taking the same rod and place the left end at the origin let the right end sit at x equals L. And then we can ask, now at our point P, up along the y-axis, what is the electric field up there? We'll choose 1 dq label your distance r. We'll just quickly go through the problem solving steps this time. It is located at the position x along the x-axis, and this point P will be a generic distance y above the axis. So it's the same object, same uniformly charged rod. Same charge Q, length L, density lambda will be Q over L. And we can ask, what is the dE, which would be produced by 1 dq, sitting down here. That vector will have magnitude k dq over r squared. In our case, r squared, this is the hypotenuse of that right triangle, is just x squared plus y squared. The amount of charge sitting in the dq, as we said earlier, is lambda dx. dx is the width, again. But now you see that our dE vector has two components, a dEx and a dEy component. Starting with the y component, we need to label our triangle here. I'll use theta to represent that upper angle. In this case, the y component then will be dE cosine theta. Our dE again is k dq over x squared plus y squared. The cosine of that angle is the adjacent side over the hypotenuse, y over r. Later, we will need sine of theta, which would be the opposite side, x, over the hypotenuse r. This is our dq times the cosine theta here, y over r. We have k lambda dx y over x squared plus y squared to the 3 halves. R is the square root of that. To obtain the full y component of the electric field at that point, we need to integrate or sum up all of the contributions dEy. Can take constants out front. K lambda y is not participating in the x integral. Dx x squared plus y squared to the minus 3 halves. Performing that integration leaves us with k lambda y x over y squared, x squared plus y squared square root. Evaluating the limits of x from 0 to L, makes the entire expression 0 at the lower limit. So we simply have k lambda L over y. One of the factors of y cancels out. L squared plus y squared under the square root. So this is your y component of the E field. We'll treat the x component with the same process, only take the sine of theta. Note also that the x component points to the left, so we need negative dE sine of theta, which is negative k dq over x squared plus y squared. Sine of theta is x over r. So we have minus k lambda x dx on x squared plus y squared to the 3 halves. The full x component of the vector is the integral sum of all of those dEx contributions. So we have minus k lambda integral dx x squared plus y squared to the minus 3 halves. I forgot limits up here, again 0 to L on the integral, and evaluating that integral leaves us with minus k lambda negative x squared plus y squared to the minus 1/2, 0 to L, or minus k lambda 1 over y minus 1 over the square root of L squared plus y squared. This problem gives you a perspective into the two-dimensional nature of the electric field now when we ask off the axis of the endpoint here, what is the total electric field. You can see as you start, if you start at the left end of the rod, the dq would create a dE that points purely up. And as you swing out and cover all of these dq's, your angle is changing all the while. The vector sum of the infinite number of those dE's turns out to be the vector whose x and y components are solved for here.